Welcome back, quantitative analysis students. It's time for your second lesson out of chapter 9, which is really the most important part of all calculus derivatives. This is probably the foundation lesson that everything will stem from. This is kind of important material. When we go into other topics, everything is going to come back to remember how to do the derivative, because the derivative is kind of the cornerstone here of calculus that we're going to use in quantitative analysis. So here in chapter 9, we're doing chapters 9.3 and 9.4. The first one is rates of change with derivatives. And then, of course, we have derivative formulas. First of all, what is an average rate of change? And what is an instantaneous rate of change? I want you to look at these things as if they're elementary 6th grade math topics. It's simply the slope. That's all it is. It's a very simple, basic idea. It's take 2 points, do a little formula, and you get a special kind of measurement about the slanting of the line that you're looking at. When it comes to slope, though, you may recall when you were in algebra class learning that the slope applies only to lines, to linear functions, things that have y equals mx plus b as their template, meaning m is the slope. And also you might recall learning that the slope is constant no matter what 2 points you choose. And that comes along when you're studying how to write equations of lines and things like that. The reason why I'm bringing that up is because that is the case with slope when you're talking about linear slope. Average rate of change is the answer to, well, what if it's not a line? Then what would the slope be? Well, take a look at the curve that we see right here, okay? This curve right here and the specific pink line that's drawn there, if I pick 2 points on this curve, and again, they like to try to, I don't know how I got zoomed out again. They like to try to make it look complicated. It's not that complicated, but this is just a point with 2 numbers, and so is this, okay? And this right here in a very deep way is just the slope of those 2 points. It's y2 minus y1 over x2 minus x1. If you look closely, you might be able to connect it to what you know about the slope formula. And since this particular line happens to it's the best thing we could do from one point to another on the curve. In other words, the line itself is not the curve. The curve is the black line that you're looking at. And further, if I was to take 2 points, like say maybe this one, and like say maybe this one right here, and connect them, would it have the same slope? Take a look. Would it have the same slope? The answer is no, it would not. And you probably could imagine using your intuition and your analytic ability that every 2 points I choose will yield a different slope again, won't it? Yes, it will, because the line is curved. It's not straight. If it was a straight line, any 2 points would give the same number every single time. But it's not curved. But it's not straight. It's curved. So every 2 points I give, again, are going to give yet a different measurement. That's why when we ask you to find, we never ask you to find the slope of a function. There is no such thing. There is only the average rate of change from one specific point to another. And the way that we deal with it is we take those 2 points and we simply apply the slope formula the way that you know it. You just apply the slope formula the way you know it. And then you could state with a lot of confidence the average rate of change from point A to point B on this curved function is this measurement. In other words, the slope of the line that would be straight between the 2 points on this curve would be this, okay? So I want instantaneous rate of change and average rate of change to be very simple, basic ideas. You already learned how to do the slope. It's just a matter of taking 2 points off of that function and finding the slope of the line that goes through those 2 points. All right, so let's see if we can put that into practice a little bit. Here's an example. Notice the average rate of change down there is very similar to y2 minus y1 over x2 minus x1. Here's a question for you. Suppose a company's total cost in dollars to produce X units of its product is given by this formula. Now find the average rate of change of the total cost for the second 100 units produced. It's kind of mean, but to say the second 100 units produced means the 100th unit all the way through until the 200th unit. Now, how do I go about doing something like this? Well, I have x values. I have x equals 100 and x equals 200. Let me set myself up with that. I got 100 comma something, and I have 200 comma something. Now, how can I figure out what the y value will be? Well, it's actually really not hard at all. All I have to do is take 100 and put it into the function c and get an answer. And it'll tell me what the y value is. Same thing with 200. And even better, why bother to do that here with a calculator when I have Desmos? Let's do this in Desmos. Go over to Desmos and get these values using a table. Let's see. Okay. Let me put the function in. Y equals 0.01 x squared plus 25x plus 1500. All right, the reason why I'm doing this is because I want to find out what happens when x is 100 and when x is 200. So I'm going to click in the formula I just typed in. I'm going to click the gear and say, please give me a table so I can get values, Desmos. Thanks. What happens at 100, Desmos? What happens at 200? It's quick and painless. There they are. So I have 2 points, 100, 4100, and then I have 200, 6900. Let's go back and put them into our formula. Well, I think I lost the formula, but that's okay. 100, 4100, and then 200, comma 6900. All right. So you want the average rate of change for the second 100 units produced. That means for unit 100 to unit 200. So what I'll do is I'll put all those numbers in. Now look at the formula for average rate of change. A is going to be 100, B is going to be 200. So the bottom looks kind of like this. The top is going to be those other two numbers. So the top is going to look like this, 6900 minus 4100. Okay. And then you're going to go ahead and figure that out and get an answer. You get 28. All right. So again, I want it to be that the average cost, the average rate of change is a very simple slope approach. That's all it is. Take a look at example 2. We're going to do a little bit with a table now. This figure shows percents of elderly men and elderly women in the workforce in selected years from 1970 and then projected to 2040. Find and interpret the average rate of change of the percent of A, elderly men in the workforce, and then B, elderly women in the workforce from 1970 to 2040. All right. So one thing that we have to do here to get this right is we're going to have to very carefully examine this graph. Let's look closely at this graph. In this graph, I'm seeing for the men, which is the blue numbers, I have 26.8 versus 17.3. And then for the women, I have, I'll use green for that. For the women, I have 9.7 and 10.1. So these are the points that I'm going to use. First, for the men, I'm going to use the year 1970, oh wait, the higher year, 2040, and then the number for the men is 17.3. The other year of data I have for the men is 1970. And I'm using, for the men, 26.8. Now for the women, I'm going to use the year 2040, but I'm going to use the number associated with the count for women, which is 10.1. And then I'm going to use the year 1970. I'm going to use the figure 9.7. All right. So take a look, friends. You'll take that graph, try to decipher what they're asking about, and you're trying to find the average rate of change from 1970 to 240. So we're going to put these into the formula, and we're going to find the differences on the top will be the y's, and the differences on the bottom will be the x's. Let's do the men first. For the men, the top is going to look like this. I'll do it up here. 26.8 minus 17.3. And that'll all be over, of course, 2040 minus 1970. Like so. And divide it. There's your average rate of change right there. For the women, we're going to do the same thing, plugging everything in the same way. except we're going to use the women's figures. So for the women, the average rate of change would look something like this. I think I got them backwards, don't I? Yeah, I did. Hold on. This one was supposed to be, the 26.8 number is 1970. Okay, there we go. Let's just fix that. Okay. There we go. Now let's do it for the green, and I'm going to do it in two different ways to illustrate a point. All right. For the women, it'll be and then it'll be 2040. 70. Okay, guys, I want you to look closely at the way that I'm doing this because there's a really good mathematical principle here that will help us to understand what we're doing. One thing that is important is that you stick to, so if you're going to make it that the first point is 2040, 17.3, and the second point is 1970, 26.8, take a look at how these connect. See these numbers connect, and then these numbers connect? You should have them connecting in that way such that you have the 1970 and the, see what I mean? And if you want to go in the opposite direction, that's cool. You go in the opposite direction. Let's say instead of doing 1970 minus 2040, we want to do 2040 minus 1970. Well, just make sure, if that's the case, that you connect the 2040 with the figure for 2040, and likewise. See what I'm saying? So the point is, it doesn't matter which one you put first or last. It will work out the same way either way because of the way negative numbers work. All right. Okay. So anyway, once you're through with that, I don't know what happened there. Once you're through with that, those are the figures that you should get. And remember that this is supposed to be percents, you know, so if this is supposed to be percents or average rates of change, or the way that they say it, if it's in dollar amounts or what, make sure you put your answers in the correct format and use that as part of your answer. Okay, now I hope that that makes sense. That's the beginning of the idea of rates of change. Ultimately, like I said, friends, it is the slope in disguise, so don't let it confuse you. All right, let's take a look now at the concept of the derivative. Now, the derivative is ultimately kind of like the next step up, if you understand progression in mathematics. After you learn this, then you learn that. Then after that, you got down, then we could teach you this. Then once you're good at that, then we can so on and so forth. Now you're ready for derivatives. Okay, what is a derivative? Well, in a lot of ways, derivatives apply to science, and you're going to hear a lot to science as well as other things like geometry and economics. And here in quantitative analysis, you're going to see cases where you're supposed to apply the concept of the derivative to get answers. At first, when you find the derivative, it's a challenging thing because it involves a lot of complicated algebra. However, the good news is, you know, you're only going to do some basic ones, and still we're gonna be able to make it through them. But for the most part, it's only temporary, and there are very quick, easy tricks to derivatives. Those of you who've taken calculus, you probably remember the power rule and all different kinds of rules to make derivatives quick and painless. But before we give you those little tricks, we do have to drag you through this very difficult thing called the difference quotient, and you're looking at it here in 4 different versions. Here, you're looking at the difference quotient given in terms of physics with regard to what the velocity is. Here, you're looking at the difference quotient in terms of the most central focus of it, which is the very derivative. Here, you're looking at it as the idea of a margin. Margins are derivatives. You could consider it to a marginal revenue or a marginal cost or a marginal profit. Those are all margins. Margins are revenues. And last but not least, in geometry, if you have a curve, you can find the slope of the tangent line to that curve given any x value of a point on that curve, also using the derivative. Now, the reason why I've collected these little green rectangles and put them all here is because they are kind of scattered throughout your book, and they never exactly tell you the secret that, guess what, it's the derivative again. It actually is somewhat intimidating. Say, okay, let's do physics. Here's velocity. Oh, okay, let's do calculus. Here's derivatives. Let's do economics now. Here's revenue. It's like, why are we doing so many different things? But if you know it, if you have a little background, the story is all of these things boil down to taking a derivative. So I want you to remember this, guys. If you see a word problem that says, let's talk about the velocity, say, oh, that's the derivative. We're going to find the marginal profit for that means derivative. I'd like it if you could find the slope of the tangent line to this function derivative. Okay, so all of those things are examples of how of why you would use the derivative. Now, let's look closely at the derivative. What is the derivative? The derivative is use of the difference quotient. The difference quotient is really actually just this piece right here, and then you're finding the limit as h approaches 0. H being basically the difference in the x values, the difference in the x values that you saw before when we were studying the average rate of change. So let's apply it first to the concept of physics, and then I'll show you how to use the difference quotient to get some solutions. Suppose a ball is thrown straight upward so that its height in feet is given by this equation, and we have an ugly equation there, and say x is in seconds. Now find the average velocity from x equals 1 to x equals 1 plus h. This is kind of abstract. It would be easier if we were finding it from 1 to 100, or a number that's concrete, that's easy for us, but it's a little abstract. It's 1 plus h. Even so, don't let it bother you too much. The point is, if you find the average velocity, that's the same as finding the slope. And if you're doing it from x equals 1 to x equals 1 plus h, then imagine that on the bottom, you're going to do x2 minus x1. That would look like this. So what is that when you subtract them? 1 plus h. Oh, wait a minute. I have it backwards. Sorry. You're going to do 1 plus h minus 1. Sorry, guys. I'm not trying to confuse you. It's a little tricky to explain without a chalkboard. All right. Anyway, if we do the average rate of change, can you see what would happen when you do y2 minus y1 over x2 minus x1? These are the x values. x2 is 1 plus h. x1 is 1. What happens when you subtract them? What do you get? You get this. Right here, you get h. And in the bottom of the difference quotient, you'll always have that h because it represents the actual change in x. Okay, so if x was 1, and then, or if x was anything, it was 79, and then you added h to it, it would be h plus 79. And when you subtract them, what do you get? H. So the point is, anyway, the difference of x's is always going to be h with the difference quotient. However, to figure out the two y's, what I'd have to do is take this right here and put it right into the position of x everywhere I see it. And then repeat again for f of x, because f of x is not hard to find, you know. That would be f of h. So if we figure that out, like we would find f of 1. So then the next thing you do is put 1 in there. I'll use blue. So then we'll put 1 in. So you figure out f of x, but put 1 in all the positions and then subtract them. In a very complicated way, that's what this is saying to do right here. It's saying, go ahead and plug in 1 plus h into the formula, find out what that is. Then go ahead and plug 1 into the formula. That's what this piece is. Find out what that is, and then subtract them. When you're done, divide by h. Now, this is an algebraic procedure that's a little bit lengthy and ugly. But when you go through doing it, you do find yourself in a position where you get a simple answer back. It's an algebraic expression, and it looks kind of like this. So let's pretend for a minute that we put all of that math into that position. When we take our break, which is just going to be in 5 minutes, we're going to take a couple breaks today because I have to write some calculus and take a picture and show it to you. We're going to go through the actual algebra of how we get 32 minus 16h. I have to write it for you, though, and take a picture of it. Basically, you're substituting in f of 1 and then f of 1 plus h. And then on the bottom, you have just h, and it all cancels out. And then you take the limit as h approaches 0. Now, those of you who've taken calculus, you can look at f of x, 96 plus 64x plus, and say, oh, I know the derivative. It's 32 minus 16h. You know, there are a lot of you that probably could see that because there are very simple shortcuts to finding derivatives. Here, before we do that, and in every calc class, before you do that, they make you do it with the difference quotient using a limit. So I'm going to ask you to give that a whirl on our break. See if you can figure out the answer to part A by plugging in these two things for the x values. It might help a little bit if you consider this to be h plus 1 plus h, and you consider this to be f of 1. And then when you're done, you're going to substitute 1 in there. In other words, put 1 right here, and you'll get the answer for what comes next. As you can see, it's supposed to be 16. If you put a 1 in there, it should be 16. Yeah, that's incorrect. So let's take a look at it. We'll take a little break. It's 5 o'clock. I'm going to ask you, please try to do that. Okay, let's substitute in 1 plus h, subtract them, divide by h, and see if you can come up with 32 minus 16h. 5 minutes and we'll be right back, guys, okay? And welcome back. So why don't we think about now what it would be like to take this function f of x equals 96, etc., and find out what happens when x is 1, find out what happens when x is 1 plus h, and apply this formula right here. Okay, let's do that. I'd like to show you my writing now. What I did was I started by copying down the original formula. Now, in this particular case, the formula is going from 1 plus h to 1. So the difference quotient in the derivative formula looks like this. Now, first of all, on the bottom, we have some basic arithmetic here, basic algebra. You should know that that does boil down to h. That makes sense. But on the top, this is a little bit ugly. This I could find. This is not that hard. In fact, I did that. I'll use a different color to show that one. I'll use green for that. I did this one. This is just arithmetic by plugging it right into the formula. Here it is. And when I was done, I got 144, which is why 144 is here. This part, though, right here, this is a little bit tricky, so I need to talk to you about how we get this one. F of 1 plus h means in every position that you were seeing x, you're going to write 1 plus h. That's why it's not 96 plus 64x minus 16x squared. In the red boxes, I insert the 1 plus h. And now we have a whole algebraic mess to solve and finish up. Here, we at least know that we have a distributive property that goes like this, quick and easy, right? But this is squared right here, so watch out for that. How does that work? Well, I have a little bit of a think cloud here to share with you. Look at my think cloud. How do you do 1 plus h squared? Remember doing this back in high school? You write it twice, and then you do FOIL. So yes, you get this nasty long trinomial here as your solution, and you could see that I did insert that right here. It's all this stuff. As I mentioned, when I did the distributive property, you could see I first screwed up, but I didn't put 64h, but I put it in. But now all of this algebra that's written here, if you simplify this, the number 144, let me use a different color to cross out. That would be better. The number 144 knocks out nicely with 96 and 64 and 16. All those numbers all collapse to 0 if you add them all up. Then we have 64h minus 32h. Talking about here, 64h and 32h negative. Guess what they come together to make? 32h. Likewise, I have negative 16h squared, which is what this is. And now don't forget it's all over h. So we could factor h out and then cancel h out, and then you're left with this. So the average rate of change is simply that. Now, if you take the limit as h approaches 0 of that, now you have a derivative. But at first, the correct answer is 32 minus 16h in that way. Okay, so the good news is you don't have to be able to do this. This is not what it's really all about. This is the backbone of it and the reasoning behind why we're allowed to take our liberties and use those little derivative tools that we know. But you will have to work out a couple of them or fill in the blanks a little bit here and there in WebAssign just to demonstrate that you realize the idea and to show off your algebra ability a little bit. But this is a typical, I would argue, a basic derivative case where everything kind of cancels out just right. And for the most part, you can rest assured that all of your derivatives will be just like that in the case of the difference quotient with the limit, because we're really just trying to get you to get the idea of it. If you take Calc 1, they give you much more advanced things with more advanced mathematical structures like square roots and fractions with denominators and things like that. So anyway, Now that we know that, the instantaneous velocity is going to be 32. And the reason why is because, let's take a look one more time. If you take this function that I just found right here, and you cross everything out the way you're supposed to, then you're left with just this. And if you find the limit as h approaches 0 of just that, you get 32. So the instantaneous rate of change is actually the very derivative itself. The average rate of change is the expression, the numerator, when you're done, 32 minus 16h. But that instantaneous rate of change is when you let it go to 0. And if h is 0, clearly this becomes 32. All right. And what does that mean? That means the derivative of the function is 32 minus 16h. And in the case where you have a point where there's a 0 difference, then you have an answer of 32 for your slope. All right, here we have another great example. Suppose that an oil company's revenue is given by this equation, where X is the number of thousands of barrels sold each day. Find a function that gives the marginal value at any value of X. Big secret, find the derivative. So in the same way we just did that, using this and using this formula, friends, I'm going to give you 5 minutes, and I'm going to ask you now to do it to this formula. So you can get a pencil out and go through the work of using that formula and putting in the values. You're going to use X and X plus H. In the last one, we used these interesting 1 and 1 plus H. This time you're going to use X plus H and X, okay? So let's see if we can get that done. 5 minutes, and then we'll show the answer to that one as well, all right? We'll come back at 5:23 with the solution. Okay, friends, coming back and taking a look at this function, let's repeat the function once. Here's the function right here. If this is the revenue, please find the marginal revenue. By the way, the marginal revenue can be expressed using this interesting notation. We say out loud, R prime of X, meaning the derivative of R, or in this case, the marginal revenue. All right, so let's find the marginal revenue for a function where the revenue is 100x minus x squared. If you took calculus before, you could see it's 100 minus 2x. We'll show you that trick in a minute. Meanwhile, if you're going to do it the hard way, your best bet would be to start by trying to figure out what is f of x plus h, or r of x plus h, and that's what I have here. And what that means is everywhere that you see one of these x's, you're going to stubbornly put this expression, which is why it looks like this here and here. In fact, you should see that that second line perfectly emulates the first line, except x has been changed with x plus h. A little mention about the confusion of that. A lot of students don't like it, that you're changing x into x plus h. It's like changing 7 into 7 plus 2. It's odd, but that is the trick to how to figure out derivatives using the difference quotient, is replace that x. If it helps you, use a different model instead of x. For example, what if this function didn't say r of x, but instead it said, let me get cute here. It said r of star. Well, r of star is 100 star minus star squared. So whatever the star is, you're going to put this into the position of where each star is. You see what I mean? So if you don't like it that it was x, and I don't like it's x, or is it x plus h? Which x is x? And are they different? Are they the same? They're not the same. X is just the model. Think of it as r of Mickey Mouse, or r of something is 100 something minus something squared, whatever that something is. And now I could put x plus h or anything I want in there. It kind of doesn't seem as ugly as it was before. So consider the first thing something of a model. Now, we're going to put everything in there. By the way, once again, that horrible algebra comes back to haunt you, of how you're supposed to do square a binomial. Here it is, right? And we go through the motions of writing it twice and doing FOIL, and we get that ugly thing. Not that different than the last thing we got. There it is. And I'm going to use that right here when it's time for me to write that expression out. Meanwhile, I can distribute right here. Oops. Right? And I get this stuff. And now I can distribute the negative here. And now I've got all this stuff. That is the revenue function with the change being h. Okay, now let's find the derivative, the marginal revenue. The way we would do it is we'd employ the formula that we know, the limit as h approaches 0, and we are going to use this formula, and in the position of f of x plus h, you'll see I have this whole experience here, and I put it right here. Then in the case of f of x, I have minus f of x. So I put all of f of x just the way it is here. By the way, notice this is the same thing as I just got, because f of x is f of x. You don't have to think very hard. And then if you distribute the negative through, it does become this. And then if you start knocking things out, everything knocks out. I'm going to use a thick line to knock everything out. First of all, x squared, x squared is going to knock out with this negative x squared. Likewise, negative 100x is going to knock out with positive 100x. And all I'm going to be left with now are these three terms, 100h minus 2xh minus h squared. If you factor those, and I'm going to write what it would look like if you factor that up top. If you factor that, it's going to be h times 100 minus 2x minus h squared. Let me just put a 2 up there. Right? Wait, there isn't a squared there. My bad. There isn't a squared there. So if I do that, and it's all over h, right? Then what happens is, of course, these knock out. And now you have this as your final thing. And if you take the limit as h approaches 0 of that, put 0 into every position you see in h. So what's the end result? The h goes away, and you're left with 100 minus 2x. Okay? So calculus, a little tricky, but you have to look at it closely and follow it. I hope if any of you are having issues following this, you'll let me know after class. I will repeat this if it helps you. But we are expecting that you're in a position here at the ripe age of college level quantitative analysis too, that you're able to handle this kind of algebra. If anything, it's just for the introductory part of how to find a derivative. We're going to do tricks after this, but you still need to know this concept. Okay? All right, let's carry on. So you could see here the derivative, like we have explained, is 100 minus 2x. Now find the marginal revenue when 20,000 barrels are sold. Now be careful because the barrels are already in thousands. See that? So that means that you're going to put a 20 right there for x, 20. And what do you get? You should get 60. But remember, the revenues are not in dollars, they're in thousands of dollars. So that thousands of dollars comes back again to haunt you right here. Let me underline that too. Actually, the reason why you're going to put 20 in is because the barrels are in thousands, my bad. And the reason why the answer is 60 grand is because you got 60, but the revenue was in thousands of dollars. They're both in thousands. And anyway, just you have to know that that's part of the aligning the data stuff that you need to know. So all you really needed to do was just take this function the way that you found it, r prime of x, after you found it, and then take the number 20 and pop it right in there, and get, when you get out, you're going to get a 60, but know that that is in thousands, so it's 60,000 is what we were looking for that question. All right. Okay, very good. I hope this is making sense. Here's another couple of little examples associated with it. This one has got to do with a little bit of geometry where we're finding the slope of a tangent line. First, let's talk about what is a tangent. Let's pretend you have this beautiful function, and it's just this great, beautiful curve going on, and then you have a line that touches it in exactly one place. Now, I'm trying really hard to do to be on top of it, but that place where it touches it, let's pretend it only touches it exactly one place, and that dot itself is called the tangent. And the actual line itself is a tangent, and that's the point of tangency. And that means that it touches the curve in exactly one and only one place at that very, very point. So when we say find the slope of the tangent, what that means is there is a function, y equals f of x, it's x squared. You know what that looks like, it's a basic parabola. What is the slope of the tangent line? Means take the derivative of that function and put the x value in, and it will tell you the slope of the tangent line. In other words, what is the derivative of, what is the derivative of x squared? Now you could go through the motions of doing it with this formula, and you will find when you're all through doing all of your algebra that the answer is 2x. I'm not going to waste your time with that, but I encourage you to do it. I think you should try to work through that. If the derivative is 2x for that, which it is, the way we would say that is f prime of x is 2x. So now what you want to do is find f prime of 2. Because 2 is the y value. And if f prime is 2x, then it's 2 times 2. And your answer is 4. The answer to this question is 4. So, yeah, I wrote it right in the middle of everything, didn't I? In other words, if you put the 2 in, you get the 4. So what is the slope of the tangent line? It's just the derivative again. Big secret, it's the derivative again. All right, now, the next thing is let's find the derivative of the tangent line again. That's what this is. So this is a similar concept. We're asked to find the derivative of this function using the limits, or using whatever method you might know. And then when you're done, identify that that is the slope of the tangent line, and pop x in there. Substitute 1 in for x and see what you get for your answer. And then when you're all done, it's telling you now find the equation of the line that is tangent at this point. So here's your plan of action. You're going to start by doing the limit situation and getting the derivative. When you do that, I'm not going to waste your time again because we did 2 examples of that. When you do that, you're going to get 6x plus 2. Now, that is the derivative. If the derivative is 6x plus 2 and you want to find the slope of the tangent at the curve at 1, 16, that's telling you that you're going to need to put that 1 there, come on. This 1 right here, you're going to put it right here. And when you do that, what do you get? You get 14. Oh, 14, where did I get 14? When you put a 1 in there, you get 8. Right, my bad. All right, so in other words, what is the slope of the tangent line at 116? It is 8. Now I want you to try to think about what that means, okay? Here's the graph that we're talking about. And here's the parabola that we're talking about with my, I'm trying real hard to draw a nice parabola, right? And we're talking about the specific point 1, 16. 1, 16 isn't, oh, yeah. See, here's the function. Let's pretend it's a basic parabola. At 1, 16, there's a point, and then there's going to be a tangent line there. What is the slope there of that tangent line? So if you're trying to find the slope of that tangent line, what you do is you put that point in, and it'll give it to you. Now imagine if I said, what is it at -1 or at -3? You know that a parabola curves this way. The tangent line is going to change as you go through, picking different points on that line that are tangent, which is why the slope of that tangent line is variable. It varies based on what point you're using. And when you look at the point you want to use, take the x value from it and put it in the formula. It will tell you the slope of that tangent line at that very moment in the parabola. So let me get rid of that ugly parabola. All right. So now that we have that, we have that the answer is 8. Now we need to find the equation of the tangent line. So here we have a point. We also have the slope of that tangent line. So you're back in the 9th grade. What happens when you have a point and a slope? You use the point slope formula and go through the motions of doing the point slope formula from the 9th grade, and surprise, you get an answer like this. So this is the kind of thing that is a little bit easier to deal with it when you're not doing it with a limit. I wouldn't have given you this until after you learned the tricks, you know, but in example 6, they're expecting you to go all the way with doing the limit, finding the difference quotient and then finding the derivative that way, then plugging in the 1, realizing that is the equation of the slope of the tangent line, then using that slope along with the point given to find the equation of the tangent line. Okay, if anybody needs to see that done, I'll do that after class today. I'll work through it with you guys on a piece of paper if you need to see that. But for example 6, everything that you need to see is right there in your textbook, written clearly, one step after the other, to get these answers. So I hope that that's clear, and I hope that that makes sense for everybody. All right. All right. So now what we're going to do is we're going to jump into chapter 9.4. But before we do that, friends, I want to take a short break. We've done a lot of math. I'm only going to take a 10-minute break because we keep on stopping. We'll come back at 5:47, and at that point, I will show you all the tricks of derivatives. And like I said earlier, we are planning on getting out a little bit early today because the tricks are kind of quick. I don't think they'll take more than about a half hour for me to show you. Okay, so right now, 5:37. Let's return, friends, at 5:42. At that point, we will go through the concept of the power rule. Welcome back, students. Let's come and finish now chapter 9.4. We're going to start doing tricks. We're going to be able to find derivatives quickly and easily without using the difference quotient, without using limits. I want you to look at it in the same way that you looked at exponent rules, or if you've ever studied logarithms, or trig, sine, cosine, and tangent, how there are facts that you can always use, and then you can apply facts to certain specific questions, kind of like theorems or axioms or properties that you already believe and know, that when you see something, you say, I know, I'll go and use that tool and solve this problem with that tool. That's what's going on with the tricks to derivatives. The first and most important rule associated with derivatives and shortcuts is the power rule. So let's talk about the power rule first. This is the basic format of what you would do to solve and find a derivative. And we did a couple of them, but if you do them, you'll start to notice a pattern. Okay, so let's take a look at this pattern for a minute now. And this is all right out of your textbook. I didn't make this up off the top of my head. It's right out of your textbook, this stuff, and it's a very good explanation. If the derivative is x squared, well then if the function is x squared, well then the derivative will be 2x. There is a pattern there. If the function is x cubed, then the derivative will be 3x squared. There is a similar pattern there. Let's do with purple now. If the function is x to the fourth, then the derivative is 4x cubed. One more time, right? If it's x to the fifth, you guessed it, it'll be 5x fourth. So what's happening here? Is this something that I made up? I'd like you to, everybody do it just what I say. No, this is naturally kind of what happens when you take the derivative. When you take the derivative, if there is a power, the answer has a coefficient that is the same as the power. It's a miracle. It makes things very easy. As long as it's just x to a power. And there's a long story about what if it's something else to a power, that's called the chain rule. We're going to get to that. But for now, the way I want you to look at it is if I have x to any power. Now, right now, these are simple powers, 3, 5. You know, you're going to do powers like 0. I think one of them today is 8.12. You'll have fractions. You'll have negative fractions in there. And very often in calculus, you're adding 1 or subtracting 1 a lot. But that's something you're going to need to do is subtract 1, because notice when it was x squared, it became x to the 1. When it was x cubed, it became x squared. When it was x to the fourth, it became x cubed. When it was x to the fifth, right, it became x to the fourth. So what is the pattern then? The pattern is, if you have x to a number, the derivative is the number times x to 1 less than the number. So it was x to the fifth, it's 5x to the fourth, and so on. And you could apply that to x to the 5,000th power is 5,000x to the 4999. That's the point. And it's something really great that we can hold on to, kind of like the same idea as how we hold on to the limit as x approaches infinity of 1 over x is 0, when that's the only thing we have. This is another thing. This is kind of the only trick we really do have. The other tricks kind of are cute and you kind of can assume them, but this is the most important trick, and everything kind of does come back to this again. So can we remember this power rule? Let's come up with a nice structure for the power rule. If the function is x to a variable, x to a number n, then the derivative is n times x to whatever one beneath that was. This is called the power rule. And this applies to any constant power, as long as you have x to that power and not something funny to that power, but just x only to that power, it works. Let's do some examples of that now. I told you that was pretty easy, right? That's how you should be able to get quick answers. Starting with the most basic concept, of what happens when it's a number. You know, let's start with that. Well, if it's a number, actually they didn't do the number, they'll do the number later. That's a little tricky. Let's do these first, all right? So in the case of y equals x to the 14th, it should come clear. This is the derivative that you're expecting, is it not? All right. In the next one, we have a negative exponent. So don't let it trick you. When you got 13, didn't you think about 14 minus 1? That's how you got 13. Okay, now let's do minus 2 minus 1. Careful. Minus 2 minus 1 is minus 3. So you're going to have an uncomfortable answer. Yeah, welcome to calculus. There's your answer. Just don't let them trick you. Think of it that way. They're trying to get you. Don't let them get you. A lot of students will say, oh, negative 2 minus 1. That's 1. No, it's not. Negative 2 minus negative 2 minus 1 is negative 3. 2 minus 1 is 1. So watch out for that. How about in the case of y equals x? Well, don't forget that y equals x is really y equals x to the 1 power. So is that not 1x to the 0? Is what we're going to get there. Now I have a deep trivia question for you, my friends. What is x to the 0? It should be like that if you're in calculus. X to the 0 is 1 every time. Anything to the 0 is 1. 500 billion to the 0 is 1. The quadratic formula that you know and love to the 0 is 1. So anything to the 0 is 1, including x. So when you do your derivative here for part C and you find the exponent is 1, drag it to the front. It's 1x to the now. What's 1 minus 1? 0. So what is x to the 0? We just talked about that. It's 1. So this has just turned into 1 minus 1. I'm sorry, 1 times 1. And guess what that is? It's 1. Okay. So for this particular case, the answer is 1. Then, last but not least, we have a very ugly fraction there, 1/3. So now I have a big trivia question for you. What is 1/3 minus 1? A lot of students are going to think of it in terms of geometry, where you have a pie with three parts in it, or if you do 1/3 minus 1 and change it to 3/3 and so on. Bottom line is, however way you want to look at it, 1/3 minus 1 is going to yield -2/3. And yes, my friends, welcome to calculus, where even your exponents are negative fractions. Okay, so just get used to that. It is ultimately just the same template. It's the same basic idea, is that take the exponent, make it the coefficient, rewrite the variable x, -1 out of it, and then you'll have your solution. These are great examples. I hope you'll come back and look at example 1 when you're trying to do your derivative rules in WebAssign. All right, let's look at example 2 now. Let's use some different letters. And also, by the way, do you remember the connection between roots and exponents and denominators? Well, some of these are pretty straightforward. U of s equals s to the 8th. You might as well call it y equals x to the 8th. I think I know it's going to be 8s7, right? And the next one, 2/3 minus 1 is the ugly -1/3. So A and B should come out pretty straightforward. They're not very different than the things you've seen in example 1. But when you get to part C, now you have a square root of t. How do you deal with that? Well, I'm going to give you a little example here. Let me go and get that really quick. I like this one right here. See if I got better images though. Never use this one. I just found this off of Google. Guys, take a look at this with me. In the case that you have a root, okay, let's start with this one, the cube root of b. The cube root of b is really very simple. It's just b to the 1/3 power, okay? For example, x to the 1/30th is the 30th root of x, okay? So if you want to connect this is called the index, by the way. The index is a little number that's in the little corner of a square root that always becomes your denominator in your exponent when you're trying to translate through from a root into an exponent. Likewise, if you have a power in there, it just becomes the denominator. So here the denominator is 2, and here the denominator is the numerator is 3, right? So we should be able to connect these quick and easy. The root itself is the denominator. If there is an exponent, it's the numerator. If there isn't, we just assume it's b to the 1 anyway, and it's 1/3. Now, there's something else that's important that we got to talk about here. These are some great cases. Let's take a look at this thing. Come on, zoom in. All right, so here's some other great arithmetic cases associated with radicals and denominators. Again, 3 to the 1/2, you should know what that is. That's a square root of 3. 7 to the 3/4, I can see what that is. The 3 on top is the exponent, and then the 4 on the bottom is the index. And if you wanted to, you could have first found the 4th root of 7 and then cubed it, or you could do 7 cubed and then find the 4th root. In other words, that doesn't matter which one you do first, if you root first or if you power first. Then we have the next thing to deal with here, which is an exponent that is negative and fractional. I want to focus your attention, friends, right here. This is a negative exponent for this is a negative fraction for an exponent. The negative means, and I want you to look closely at the way this connects first. Forget that it's 3/2. Pretend for a minute it's x to the -20. It's 1 over x to the 20. Okay, so whatever the negative is, you make it positive, but now it's in the denominator. Notice 1 is on the top. 1 is on the top unless there's a number somewhere. Like if this was like 3 here, 3x, blah, blah, then you'd have a 3 up top here. But you don't. Likewise, since it's a denominator of 2, that means a square root. And just in general, we never write a 2 in here. We don't write 2's inside here. We assume it's a square root, so you don't put it in. All right. D is an abstract idea that the author wrote for something, some purpose, but we're focusing on A, B, and C today. I just wanted to be clear that when you see a negative exponent, it should be in the denominator. When you see a fractional exponent, the top is the power and the bottom is the index. That's it. So if you can translate these odd expressions into strictly exponential expressions, then you'll be able to find their derivatives. So take a look at C of t now. Okay, t to the 1/2. That's what the square root of t is t to the 1/2. So when you find the derivative of that, it's going to be 1/2 times t to the power of -1/2. And that's because 1/2 minus 1 is -1/2, right? So the numerator, the coefficient is the actual exponent 1/2. And then the exponent itself is -1/2 because of the power rule subtracting by 1. Last but not least, and I'll do this one in purple, or let's do it in red. This one is t to the -1/2. So if it's -1/2, I have a very dark question for you. What is -1/2 minus 1? Well, it's -3/2. And if you take a little bit of time to figure that out, you get your -3/2. Something that students often do when they're doing derivatives like this, they'll say, "Oh, that's ugly. Is that really right?" And then they'll lose confidence. The uglier it is, the better off you are in calculus. Look how ugly that question became. -1/2 t to the -3/2. Not only do you have fractions as coefficients and exponents, they're both negative, and the exponent is improper. Welcome to calculus, okay? So this is the answer we're expecting for examples 2A through D. I hope this is helping a little bit. They're all just applications of the power rule, which ultimately states that if you have a power, all you want to do is take that power as the exponent and turn it into the coefficient and then lower the power by 1, come what may. Whether it's got a negative integer, whether it has nothing there, you can assume it's 1, whether it's a fraction, or whether it's in root form, you can change it to a fraction first. And you have to know how to do all that stuff. It's a piece of cake, right? All right, carrying on, rounding the corner here, right? Powers of x rule, here's a little bit more about that. This has to do with the tangent line. So when we were talking about the tangent before, when we did it to a function that was a parabola, here, if you're trying to write the equation of a tangent line for a graph, it's really straightforward because you know how to find the derivative of y equals x cubed. You might be in your imagination thinking of what it is already. Is it not y prime equals 3x squared, right? Yeah, of course it is. So that is going to be the actual derivative. Let me write that down here for us, okay? The derivative, which I can say is y prime equals 3x squared. Now, you might be saying to yourself, wait a minute, that's not the answer. You're right, that's not the answer. The question didn't say find the derivative. The question said find the tangent line. Now, what that derivative is a formula for the slope of that tangent line. And if the tangent line has a point x equals 1, I can certainly find out what the y value is. I know what the formula is. It's y equals x squared. In other words, there is a point 1, 1. So if I put 1 in to the derivative, it's going to give me an answer of 3. In other words, at the point 1, 1, the slope of the tangent line is 3. Let me jot that down. I could have written that better. Let me put it over here. Okay, so now that I know that the slope is 3, I know that I have a point 1, 1. I'm going to use the point slope formula. I'll write it over here for you. Y minus y1 equals m times x minus x1. And put the 1s in there. Remember that? That's called the point-slope formula. In the point-slope formula, I'm going to put all the important values in. I'll show you with my spray paint can. All right. The slope 3 is going to go right there. The value x1 is going to go right here. And then the value x2 is going to go right over there. And then I'll put them all in and figure out what I get. Let's write that out. That would be y minus 1 equals 3 times x minus 1. And then distribute there. Y minus 1 equals 3x minus 3. And then simplify, add 1 to both sides. And you'll see that you get, of course, here it is, right? All right. So I hope that was clear. That's how you find the slope of the tangent line. You start by finding the derivative. You plug the x value in to find the slope of the tangent line. Then use the same x value, 1, to the original function to find what the y value would be, and then apply the point slope formula. There is an alternative way to do this. Some students like to use y equals mx plus b, and they'll plug in x and y and m to find b. And if you do that, you'll land on -2. And then you can come back and construct it using y equals mx plus b. That's the slope-intercept formula. I'll jot that down for you guys here too. But that everybody remembers. Okay, so I hope that that's really clear and helps you guys. Now, we're going to take a short break again. I want you guys to take a look at these rules. Ultimately, what they're trying to say is if you have many derivatives added up, you could just take the derivative of each one. If you have a bunch of derivatives all subtracted, you could just take the derivative of all of them and take minuses in between them. If you're trying to find the derivative of a constant, like say, for example, the derivative of 10, or the derivative of 70, or the derivative of 1/2, the answer is going to be 0. Why? Why is that the case? Well, in the case of a constant, let's pretend you were talking about, and let's actually go there. Say you were trying to figure out the derivative of the function y equals 4, for example, in example 4. Y equals 4. Well, how do I find the derivative of that? I only know the power rule. Well, we do know that 4 can be rewritten to look like this. Okay, remember that x to the 0 is 1. So isn't it true that 4x to the 0 is ultimately 4 times 1, which is 4? So what I've done was, and this happens a lot in calculus, a simple concept like 4 is exaggerated to be 4x to the 0 for purposes so that we can take the derivative. And if you do that, what happens? Well, that derivative 0, that exponent of 0 gets brought to the front and becomes the multiplier. So to find the derivative, you wind up with y prime equals y prime equals 0 times, well, let's start by ignoring the 4. And then the 0, and then x to the minus 1. And by the way, there is a multiplier there. Let me put a little multiply sign in there. That other thing that we didn't talk about just recently is that there is a constant rule and there is a coefficient rule. The coefficient rule says if you see something that's a power but there's a coefficient, you could just ignore the coefficient for a minute, go do the derivative, and when you're done, bring the coefficient back in. So for example, if it's 4 x to the 0, forget the 4 for a minute and look at x to the 0. What's the derivative of that? Well, it's 0 times x to the minus 1. X to the minus 1, yeah, that's 1 over x, but nobody cares because 0 times it is 0. 0 times the 4 is 0. The answer is 0. In other words, the derivative of any constant will be 0. Okay? So when you're doing your sum and quotient rules, if you come across a constant in your arithmetic, when you take the derivative, just make sure that you insert a 0 in that position. Okay. So what we're going to do now is we're going to take a very short break once again. Right now it's 6:03. At 6:08, I'm going to come back and we'll talk about the answers to example 5. Everybody, please take 5 minutes and try to use the ideas that we just talked about to solve the derivatives for A, B, and C in example 5. We'll come back at 6:08 with the answers. Welcome back, friends. Time for us to go over these examples. For our convenience, I have included each question again. I'd like to illustrate with some rectangles, so try to follow along with me if you can. Starting with f of x equals 4x to the fifth. The constant rule and the coefficient rule come into play. Well, the coefficient rule comes into play because I don't know how to do 4x to the fifth. I could do x to the fifth, right? Because we know the power rule, but I don't know the 4. Well, the 4 follows along with the concept of the coefficient rule. So the way we do it is we act like the 4 isn't there for just a minute, and then we actually find the derivative of 4x to the fifth. It happens to be of x to the fifth itself. Let me use color to show that, so that that's clear. I'm trying to find the derivative of just x to the fifth, and that's going to be 5x to the fourth. See, I've ignored the 4 for just a minute. Now that I'm done, I have to calculate what's 4 times 5, and I get the 20. And the answer to this question is 20x to the fourth. I hope you got that too. All right, let's look at example 5b. In example 5b, we have a fraction, the other F word. Don't let that bother you. It's not a big deal. But again, it's just a coefficient. So I'm going to give it a blue square, or rather, it's a coefficient, so I'm going to ignore it for a minute. And I'm only going to focus on what's in the blue square, which is t squared. So the derivative of t squared is 2t to the 1. Notice that the half has not changed. I'm going to give it a little bit of an oval, the half. The half is staying there, and it's still there. See that? But now I can figure out what happens when I do a half times 2. You know what a half times 2 is. They cross out, or here we have them crossing out, and you wind up with t as your solution. I hope example 5b was clear for you, my friends. Let's take a look now at example 5c. In example 5c, from the beginning, we get a little bit intimidated looking at that nasty square root on the bottom. The square root on the bottom, first of all, means that the exponent should be negative. Further, if it's a square root, at this point, we should know off the top of our heads, square root means 1/2 power, right? And why is that? Because a square root has an index of 2, and q here has an exponent of 1. We don't see an exponent, so we assume it's 1. So the numerator of the exponent is 1, and the denominator is the index, which is 2, which is not written there. That's understood, right? So 5q to the negative 1/2 is really what p is. Notice I didn't do any calculus yet. I didn't do any derivatives or anything. I just manipulated the equation I see so that it was in a position where it was ready for me to do the derivative to it. Now I can. And remember, what I'll do is ignore any coefficients for the moment and then come back and deal with them later. So ignoring the coefficient 5, my task at hand is really to deal with the pesky q to the negative 1/2. So q to the negative 1/2 means take 1/2 and make it the new exponent, rather the new coefficient, excuse me, ignoring the 5 for a minute, and then lower negative 1/2 by 1. Look at the arithmetic I gave you right here. Look closely at this, friends. Negative 1/2 minus 1 is negative 3/2 any way you look at it. You got to get comfortable with adding and subtracting fractions, especially to the number 1. And I'll show you a trick of that just before we close today about adding and subtracting things to 1, especially fractions. All right. Now, 5 times negative 1/2 is the inevitable negative 5/2, and you can mess around with this if you want, but that's usually more than enough. Desmos will take, rather, not Desmos, I'm sorry. WebAssembly will almost always take that. Okay. So I hope that was helpful. Let's go back to our lesson. And here are your answers as promised. We got just t because everything canceled out. And then the last one was this nasty fractions and negatives and roots and stuff. There you go. All right. Now, by the way, a word, this is supposed to be negative here. Just as an FYI, it is negative, and I don't know why that's not in there, isn't it? Yeah, it is supposed to be negative. So the negative is missing as an FYI, but that's also in your textbook. You can go and look at that. All right, let's take a look at example 6 now, guys. It says, world tourism has grown into one of the world's major industries. Since 1990, the receipts from world tourism, Y, in billions of dollars, can be modeled by this function. We have a function here, where X is the number of years past 1980. Name the function that models the rate of change of the receipts from world tourism. Name the function that models the rate of change. That's elementary. The answer is, it's called the derivative. The answer is the derivative to that question. Name the function, the derivative. Okay. Next, Find the derivative. Okay, here we go. Find the derivative. This is not too hard. Find the derivative. It's just we're going to do it with decimals now, right? So we're going to do it with decimals. Remember, to find the derivative of y prime, we're going to start by ignoring that coefficient of 15.9. And then we're going to multiply that by the derivative of x to the 1.18. Start by writing the coefficient, 1.18x. And then, what is 1.18 minus 1? The answer is 1.18. So your exponent is 0.18. And then last but not least, we could take these two numbers and multiply them together. And we're going to get this as our solution. Welcome to calculus, where the answers are absolutely hideous. Look, that's the answer that we're expecting for a question like this, okay? Now, you understand the power rule. You know what to do. You know you have to multiply because the coefficient rule. You know all of that stuff. And as you're doing it, it gets uglier and uglier. So get ready, friends, for very weird numbers, 18.762. Yes, 3 decimal places we're expecting, and WebAssign will not give it to you if you round. So put it in the way you see it, okay? I hope that makes sense. Last but not least, find the rate of change in the year 2020. What that means is, notice, by the way, we are talking about X is in the number of years since 1990, right? So 2020 is how many years since 1990? The answer is 30, okay? So you're gonna use 30, right? You're gonna use 30, you're gonna put 30 right into the position of X, put a 30 in there, get your calculator out, or use Desmos and put a 30 into the table. And when you do that, you're going to get this. Problem with that answer is, remember, the actual money itself is in billions. So the answer is not $36.45. The answer is $36.45 billion is what we were looking for. So watch out for those labels too. That's something that's incorrect here, that it should have said billions or been written out of billions. All right. Now, the sum and difference rules, basically, they're nothing more than a compounding of what you've already learned. If you look at each of these questions, you'll notice that they are all just repeats of the things you already know, just in lists. The derivative of this is 3, you should know that. The derivative of this is nothing because it's a constant, you should know that. The answer is 3. The derivative of these should not be hard. You already did this one somewhere along the line. You already did this one somewhere along the line. So one more time, I'm going to ask you to take a look at them, make sure that you understand how they work. Here are all your solutions. And I'm going to ask you to make sure that you're comfortable with that. When we get together on Wednesday, I'll open up with, is everybody okay with the derivatives? Do you want me to go through some of them with you? These are the answers to those derivatives. You can use this as a guide when you're trying to do your homework, okay? Each of them is nothing more than just a repetition of what we've already studied, except that it's in a list with pluses and minuses. And as you can see, the answers are all right there in order. Like, for example, for this one, you have 4x cubed minus 2x squared plus 5x minus 3. In B, you have the 3 of them there. Don't forget that the last one is a constant and has nothing as its derivative. You see it doesn't match. For F, we have 2 different things. There they are. Okay? All right. And then an application. Suppose that T is the number of years past 1960, and that I is this ugly formula, and it's modeling U.S. total personal income in billions of current dollars. For 2018, find the model's prediction for the income. Once again, you're aligning the data. So if it's 2018 and this is years past 1960, you're doing a basic arithmetic concept, 2018 minus 1960. And you're going to get 58. So what do? Do you find the derivative? No, not yet. Don't find the derivative yet. Be careful. Look at the question they're asking you. They're saying, this is the total income. What is the total income in 2018? Don't take the derivative. Just take your number and put it right here and right here and do some calculations. You can either do a calculator or you could put it in Desmos and type in 58 into the table. And it'll give you, this is your answer. And don't forget it's in billions. The next question says, find the rate of change of the US total personal outcome. Guys, it's the language I want you to remember. The marginal revenue, the slope of the tangent line, the rate of change. They're all synonyms for the derivative, which is our primary focus today. So what they're saying is just find the derivative of it now, please. Okay, here you go. There's a derivative. Remember, by the way, the derivative of 601 is going to be 0 because 601 is a constant. So example 8 is a great application, and one of the most important facets of example 8 is you should know when to use the equation they gave you and when to use the derivative of the equation they gave you. It depends on the question they're asking. Look closely for the wording. They're saying, this models the U.S. total personal outcome. Now find the U.S. total personal outcome. That means don't find the derivative. Use the formula they gave you. Watch out for that in WebAssign. That can get a little confusing. All right. Okay, a couple little more examples, and then we're going to close. We're just about through, friends. Suppose that a manufacturer of a product knows that because of demand for his product, his revenue is given by this formula, and X is the number of units. Find the marginal revenue at X equals 500. Instead of doing it, I want to talk to you about what is your plan of action. This is the revenue function. How can you find the marginal revenue at X equals 500? Well, first find the marginal revenue, meaning take the derivative, right? If you take the derivative of this, you might be able to see in your mind's eye, the derivative of this is going to boil down to 1500, and we call this R prime of X minus, and then I'm going to do 0.02 times the derivative times the exponent 2, which is 0.04 X, and then I'll lower it by the 1. This is the actual derivative. This is not the answer to the question. This is the derivative, the marginal revenue, if that's the revenue. If I want the marginal revenue at X equals 500, that means now I need to find R prime of 500, which is going to be 1500 minus 0.04 times 500. Do a little arithmetic there, and you get $1,480. All right. For part B, it says, find the change in revenue caused by the increase from 500 to 501. Now, this is something that we have to talk about. The marginal revenue is supposed to represent, like the slope, the actual amount if you just sold one more item, or if you just the cost to create one more item, or if you made profit off of just one more item. So when you're talking about margin, the margin is the slope. And in the world of slope in algebra class, that we call it M, it's M equals. Why is it M? Because ultimately the point of slope from the beginning was money in math, margins. So M is the slope. And when you find the derivative, it's not going to be that far away from M. In fact, look at what the answer is when you go up just one more. If you go up just one more on this function, which by the way is a parabola, not a straight line, you get a number very, very, very close to what the answer was for the derivative of 500. We do expect them to be close to each other because the line curves very slowly, especially from one unit to the next, from 500 to 501. It's not much of a difference, as you can see. It's literally a 2 cents difference, okay? So if you want to find the change in revenue, basically what you're doing is you're not using the marginal revenue function, you're using the revenue function. Plug in 500, which we just did, and we got a certain amount, and then plug in 501 and subtract them, and you'll see what you get. This is the figure that you get. Okay? So as promised, I'm ending early. We are ending a little later than I thought. I thought we'd be done by 6. I'm sorry for holding you guys. I just want to make sure you have a good lesson today and early understanding, because like I said, this is probably the most important, one of the most important lessons you'll get in quantitative analysis too, okay? I'm going to stop our recording, and then I'll open up the floor to any questions you may have. In closing, thank you so much for your close attention to my lesson. I worked very hard to make it as clear as I could, and I appreciate all the work you're doing. Remember to ask questions if you need to. And this is Mr. Marqueta signing off. Thank you. We'll see you Wednesday for our next lesson.